Before we begin this screencast on manual methods for analyzing circuits, there are a couple things I'd like to clarify from the last screencast. As you remember, I used maybe a handful, dozen or so charges distributed across the circuit elements to describe how the non-uniform distribution creates an electric field that pushes the electrons through the circuit. Now, when I use a dozen or so charges, that's just to illustrate the concept. Please understand that there are Avogadro's numbers of charges throughout the circuit. There are jillions and jillions of charges, positive or negative charges, and positive charges. So, and the second thing I'd like to clarify is that not all circuit elements follow Ohm's law. There are, filament lamps, for example, LEDs, other diodes, thermistors, and other circuit elements do not follow Ohm's law. Okay, and so let's begin our analysis now of the circuit. In order to begin, of course, we need to define a circuit. So let's say that we have a 12-volt power supply. We'll put 12 volts on this end. And to make it perfectly clear, we'll say it's 0 volts on the other end. Now let's assign some values to these resistance. Let's say this is 3 ohms. We'll make this one 4 ohms. We'll make this one 5 ohms. We'll be creative and make this one 6 ohms. And this one 7 ohms. Okay, so now we've defined the values of the resistances of our circuit. As we talked about yesterday, once we turn on the circuit, current will begin to flow. And we'll describe the flow of current through this branch. We'll call that value of the current I1. It flows across the 4 ohm resistor, and so we have I1 on the other side. Where it splits at this junction and comes down this branch, we call that I2, and the other split I3. I3 continues then across this branch and so on as we described before. Now, to analyze the flow of current, we need to figure out what I1 is. That's the basic approach that we're going to do. And to do that, we have to break down the circuit into an equivalent circuit that looks like this. Okay, we're going to have a simple circuit where we have our 12 volts here, and we have an equivalent resistance here. And so it would be very simple to calculate I1. Okay, I1 would simply be equal to, well, we'd have the voltage here. V is equal to I times R equivalent. What are we doing here? V equals times I. And so I1 would be equal to the voltage, which we know, over the equivalent resistance, which we're about to find. Okay, so let's shrink this up a little bit. We'll group it and make it a little bit smaller so we have some room to work with. But this is our overall strategy. This is what we're trying to accomplish at the end of the day. Okay, so the next step now is to try to figure out what is the equivalent resistance of the circuit. And if we look at the far end, always start from the far end and start breaking it down from that end. We have the 7 ohm resistor and the 3 ohm resistor in series with one another. And the way we combine series resistors is simply to add them together. And so when we add the 7 ohm resistor and the 3 ohm resistor together, we get a 10 ohm resistor. The 10 ohm resistor is in parallel with the 6 ohm resistor. And we can find then the equivalent resistance of the 10 ohm resistor and the 6 ohm resistor as follows. To find the equivalent resistance of parallel circuit elements, we simply add the reciprocals and then take the reciprocal of the reciprocal. Did I do that right? And so the equivalent resistance for this would be 10 plus, be 16 over 60. Okay, and when we take the reciprocal of that, we get the equivalent resistance of the parallel part is 60 divided by 16. I have to do that calculation, my calculator. And we get 3.75. Okay, I'm going to shrink that up. So we have more room for calculations. We're going to group it and shrink it. So we found the equivalent resistance now of the parallel branch of the circuit. To find the total resistance, we need to add the 4 ohm and the 5 ohm resistance to that. And when we do that, we end up with the total, I have to get my pen out, we get the equivalent resistance, I guess I'll put a sub T there. The total equivalent resistance would be the 4 plus the 5, which is 9, plus the 3, which is now 12, which gives us 12.75 ohms. I'll do that one in my head without the calculator. Okay. So now what we can do is find I1 right here. Okay, we're going to use this technique now for finding I1. Okay, and so I1, well, let's just write down Ohm's law. The voltage is going to be equal to IR, and we just found the equivalent resistance, the total equivalent resistance of the circuit. I'm going to move this down a little bit. And so now we can find, let's say that's I1. So I1 becomes the voltage, which is 12, divided by our equivalent resistance, which is 12.75. And so we've found I1. Let me get my calculator. 12 divided by 12. We get 0.9412 amps. Okay, now let me set that down, and we're going to group these and shrink it. Okay, so we've completed this part of the analysis. We've found I1. Now, the question is, what do we do next? Okay, we found I1. Okay, and so the next thing we need to do is identify some of these points. Let's call this point A. Excuse me, I have to get my pen out. Let's call this point A, and we'll call this point B. This node here, we'll call that B. And, well, I probably should have had these two also. Let's call this one C and this one D. Now we're going to start looking at voltage drops across different circuit elements. So from C to A, we know that the voltage at C has to be less than it is at, the voltage at A has to be less than what it is at C. Because at C it's 12. And if you go all the way around the circuit, it ends up being 0 at the negative terminal. And so there has to be drops all the way through the circuit. So A, the voltage there has to be less than C. All right, so the change in voltage from A to C will be equal to, well, using Ohm's law, I1 times 4 ohms. Okay, and so the voltage drop from A to C will be equal to 0.9412 times 4, and I have to get my calculator out in just a second here, make that calculation. We get a drop of 3.7647. Let's use them all. Okay, and that's volts. Okay, so we found the drop now across the 4 ohm resistor. Let's group that and shrink it up a little bit, and then we'll move it down here. Let me shrink it a little bit more so we can keep it on the screen and bring it out there. All right, but what we really want is the voltage at A.